Exercise 7.12 is a little complicated to explain because it's very, very theoretical. But let me try to explain it. First of all, I wanted to make an example. So I have, for example, a ball rolling up. A ball rolling off a steep incline with height h. Okay. So, and I know that, for example, the coefficient of friction is equals to, let's say, 0.5. The mass of this ball is equals to 1 kilogram. Okay, so I can find the acceleration of this ball, but I have to do a couple of things first. First of all, I know that the force that is going to act by pushing it down is going to be the potential energy. So it's going to be equals to mgh, and this, of course, only depends on, I'll just keep it, and to find the force, I have to derive this in terms of, in our case, y. So if we count h as y, so instead of this we count it as y, it's going to have d over the y of du, which is going to be equals to mg, which is very clearly the gravitational force in the y direction. Anyway, this, though, is only one force that is applying to the ball. Another force that is applying to it is friction force, which is going to be equals to the normal force. So normal force is going to be equals to, if we call this alpha, is going to be equals to mg times the sine of, the angle is not theta, is alpha. And this is just normal force. In order to find the friction force, I would have then to multiply by the friction coefficient. So in our case, our friction coefficient would be our mu of 1. And so if I want the friction force, it would be equals to n times our mu, which is equals to mg sine of the angle alpha times our coefficient. Okay? Sorry, actually, no, it's not sine. My bad. It is cosine. I'm a little confused. Cosine of alpha. There we go. Perfect. Okay, so now to find the force friction, we know that the force friction is actually going to push in the opposite direction. Also, one thing that we have to take account of is that the plane, the ball is not moving directly down, but this potential energy is going to be broken into parts. So it's going to be broken into components. So this part here is going to be equals to the mg times sine. So the actual acceleration, the actual force acting on it, will be equals to mg times sine of angle alpha. Okay, so the actual forces acting on it will be equals to that is equals to mg times sine of alpha minus mg cosine of alpha times mu naught. Okay, and this is the force. Of course, I can divide it by m, and I will find the acceleration. So acceleration is equals to g times sine of alpha minus cosine of alpha mu, and that is the acceleration on our ball. And therefore, if we put it, if we put it equals to mass, so m times the acceleration is equals to the force, which is going to be equals to this part over here. But as you can see, actually, let me write it. M is equals to ma is equals to our force net. So we know that ma or mx double dot is equals to, actually, sorry, we're talking about in the y direction. That's acceleration in the y direction. So y double dot is equals to this part over here. And as you can see, if we get rid of all the dams, we get this answer we found before. Now, if we instead were to take the Lagrangian, we know that the derivative of the Lagrangian in terms of In our case, our y is equals to d over dt, the derivative of Lagrange in terms of y dot. Okay, so from the first part, we actually get that the derivative of this is going to simply going to be equal to the derivative of the potential energy, which is in terms of y, is that dy equals d over dt, and then the derivative of our kinetic energy in terms of the velocity. So out of the left, actually we know that this part over here, as mentioned by the book, is equals to negative force. So is equals to the force, and also we prove this right here, mg y, and if we derive it, we get the force. So we get the force right here, and then it's going to be equals to d over dt of my dot. So if there again, negative f is equals to my double dot. But this is not taking into consideration the friction force, because as you can see, the only force that is taken into consideration is the gravitational force. Therefore, in our solution here, we would have to add our friction force. So this one is actually not accounting for, in our case, actually, let's make a little more general, non-conservative forces. Okay? So if we want to account for non-conservative as well, we'd have to write negative F plus the non-conservative forces, the book calls them friction, is equals to our my double dot. And as you can see, they're in different directions because the gravitational force actually pushes towards down, while our friction force is in the opposite direction, so push towards the up. So they have to be in opposite signs. Now, of course, the friction force in our inclined plane, if we have the x and y axis like this, the friction force will actually be pointing towards the up, while the gravitational force will actually point towards the down, so the negative direction. And this is how we prove, or basically what we actually asked to prove.